Howdy folks, welcome back, and we're going to do part 6 today. And so what I wanted to do is, I think at the end of last video we discussed that the pathing system is really lame because it's not set up, that the type of maze that we're trying to go through is not set up correctly. So what I want to do is we're going to do a different algorithm for pathing. And so what we're going to do is we're going to find the whole way to get there. So what I need to do is we're going to do a let me see, we're going to go int, yeah, we're going to go bool and a two-dimensional. We're basically going to make a copy of our block thing, and we're going to go search cells. So I've got some notes over here on the side. I'll just show you guys. I've got some notes over here on the sides of what I want to do, just so that I know, because I wrote this down like last week, of how I want to proceed with this. And so that's what I'm looking at when I'm glancing over. I'm just looking at my notes to see, you know, because I totally forgot what I was going to do, kind of thing. Basically, in general, what we're going to do is a Floodfill. And so if you say the, let me see if we can start a, let's go like this. Maybe I can show you on, let me see, go like this. There we go. Okay, so we can take something like this. Let's go, we'll make a new thing here. You know, this is our grid, okay? Say this is our 45-40 grid, and the player is here, you know, and the our target is here or whatever. You know, basically you want to find from here to here, and you've got obstructions in the middle and everything. So what you're going to do is you're going to go out to each neighbor, okay? And so you're going to go 1 like this, okay? And then let me change this because that's going to drive me nuts. All right, and let's zoom in a little here too so you can see a little bit better. All right, so we'll go like this. Okay, so what you're going to do is you're going to find these, okay? And so then you're going to populate a list, and this list is going to contain all of these, okay? And then you're going to go through each of these. So we're going to reiterate this thing over and over. So for each of these, we're going to do each of these neighbors, and we're going to go 2. So for each of the 1s, every one of the neighbors of it is going to be a 2. And then for each of the 2s, every neighbor of it is going to be a 3. Okay, and I think you guys can see what's going to happen here. This is a very simplistic flood fill. And so what you're going to end up with is you're going to end up with 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and then this is, you know, you're obviously going to have 4 here, and then you're going to have 5 here, and 6, 7, 8, 9, 10, 11. So as you can see, basically you're going to end up with a whole list of these things. And so then once we've got that, basically once our flood fill reaches the target, then we'll just go to the nearest one that's, we'll just pick one, okay? And we'll pick one that is the number, the highest number, obviously, or the neighbor with the lowest number, that is. So we're going to pick the neighbor with the lowest number, the neighbor with the lowest number, that one, and we're going to basically make an array of cells that make our path back to here. And so that's what we're going to do with our variables that we're going to be adding in here and everything. That's what these variables are going to be for. And so the first one that we're going to set up is our whole array, and they're all going to be false, so that we know when we're here, how do we know that this one isn't already a 1 or a 2 or whatever, okay? And so that's what we're going to do. And actually, I just realized now that we're not going to be doing Booleans. We're going to be doing, obviously, we're going to be doing the, whatchamacallit, we're going to be doing integers. So we're going to need to change that to an integer. And so let's go to here. We'll go int search cells. Okay, and then this is going to be max size by max size. So we need to make sure that we do this. Let's see, we're going to go search stuff. We're going to initialize search stuff, and so we're going to go, before we forget, we're going to go search cells. And let me see here, where are we? Equals new int max size, comma max size. There we go. Okay, so there is our first thing. We're also going to need a trail int, and that's going to be for each one of these, right? Let me see. Enemy, yeah, we're going to have an enemy trail. So I think we're going to do a two-dimensional this way, a jagged array, and we're going to go trail, and then we're going to go like this. So let's see, enemy trail, whoops, equals new int. You know what? What am I thinking here? This is going to have to be a two-dimensional. There we go. So this is going to be for each enemy number, and then this is going to be the X and Y. So enemy trail equals new. Let me see. We're going to have to go. How am I going to do that? Enemy trail equals new. I got to figure this one out here. New int, right? And because we're going to have to go, no, we're going to have to go like this first, I think. Because I'm just trying to figure out how we're going to make this jagged array. I forget exactly how I do that. Because this is going to need to be a fixed number, right? Like that. And then it's going to be like that. There we go. Okay. So that's what I need to do. And then that's going to be, do we have max enemies? Yeah, max enemies. Okay. Max enemies. There we go. Okay. And then for int I 0 is less than max enemies. And then we're going to go enemy trail. And let me see, is that going to be, I'm not sure if I need to, actually I don't think I need to do that here. I'm going to just need to do that when I create the trail, aren't I? Yeah, so we're going to leave that for now. We're going to leave that for now. So basically we need to declare our two, let's see, do we need other ones? So we need, for our search, we're actually going to just use local variables in our search. We're not going to need large scale or the full scope for that. They don't need to be accessible from anywhere else. Okay, so we've got that. We're going to put, let me grab some tea here. We're going to put, where's that going to be? Where's our finding our, is this our AI? Yeah, here's our AI stuff. Okay. And let's see, we don't need that. I mean, because the other thing we can do is we can just do a, we can simplify our array here to a single thing. You know, we can just call it 0 through 3 or 1 through 4 or whatever, so that each item in the trail is just an up, down, left, right kind of thing, instead of being a, you know, an X and a Y coordinate. I don't think it's going to help that much. We're not using that much memory or anything. So we're just going to make it simple to begin with. And this is going to be the target. Okay, so that's where we've established our target. Okay, so we need to get rid of all this stuff here. And let me see here. We're going to go like that. That looks like the part. Okay. So we're going to cut this stuff out. And we are going to, I'm going to throw that in a notepad just in case I want it later, although I do have that online. I don't think we're going to come back to that at any point. I do have it in the branch for episode 5. So what we're going to do is we're going to go int, let me see, whoops, not that way, this way, leaf list. So what I'm going to call our stuff here is, see here, where is that? There. I'm going to call these ones here, this is going to be like our trail of leaves, and so I think that's how we're going to do it. Let me think here for a minute, and we're going to go leaf list equals new int, and I'm not sure how big I'm going to need that to be. I guess the biggest path is going to be 40 plus 40 is 80, and I don't know, it might even be bigger than that, so why don't we just go 240 for right now. It should be able to do the entire circumference of the thing. I don't think it's going to go farther than that, and yeah, I'm just trying to think of how I want to do this. Well, it's going to be 40 by 40, it's going to be 1600. We'll just give it the max. And this is going to be a one-dimensional. I'm not sure why I was thinking this is going to be two-dimensional. Okay. Is that correct? Why don't we do... Yeah, that is going to be two-dimensional. Well, it's because I want this to be linear. This is the trick here. So I think we're going to do this. We're going to go X, and then we're going to do Y. So each, whoops, and then we're going to go int num leaves equals 0. So we're starting out with 0, and the leaf, basically a leaf is an item that's at the end that has not yet been expanded. So that's basically what we're doing here. And honestly, I don't think we're going to need 1600. I think that number is too high, but what we can do also is we can just check while it's running and see how big this number gets, and then we can just limit it by that if we need it to. Okay, and so we're going to go while, let me see, we need to go bool done flag equals false, and then we can go while not done flag. So we're going to set that to true when we've either run out of spaces to Floodfill or we've hit the target. So if for each of these iterations, what we're going to do is we're going to go through our leaf list, and you know what, we need to put our target X and Y. So we're going to go 1, and then we're going to go leaf list X num leaves. Well, that's going to be 0, isn't it? I'm going to go 0 equals our target X. Okay, so there we go. It's our target S. So what we're going to do is we're going to start at the target, and then we're going to flood fill our way back to the enemy, just for reference. So let's copy this and let's make sure we get both of the Y's. Whoops. There we go. And I know I'm doing this in like meandering. I could probably have started with all this stuff, and I probably could have programmed this whole thing in like an hour. But I'm trying to, you know, go through the simple. I don't want to start with more complicated algorithms, and then for at least this series anyway, you know, I want to start with simpler stuff and then kind of show you why we work our way up, you know, why we're doing the algorithm that we're doing. So anyway, now what we have is we have our first leaf, and then we're going to go for I equals 0, I is less than num leaves. So for each one of these leaves, list, what we're going to do is we're going to Let me see here. We're going to take each neighbor. Why is this telling me I? Am I already using I? Yeah, I am. Okay, we're going to go J then. Sorry. I've got a kitty in my lap if you're hearing things. That's what that is. Kitty's over here making all kinds of noise now. Okay, so for each leaf in the list, we're going to find 4 neighbors. And if the neighbor is empty and not already used, then we give it a position number and add it to the leaf list. Okay, so these are our steps that we're going to do. It helps to break this stuff down before you start coding it. So we're going to go, I'm trying to think if there's an easy way to do this, and probably we'll just do the same code 4 times because I'm lazy. And so what we'll do is we'll go, if we need to figure out if the other thing is we need to check if any leaves left. Move self from. Okay. We need to do that too, and that needs to be inside here, doesn't it? Yep. So for each of those, yeah, we need to remove that and check if there's any left. Once it's done, I think that's going to go on the outside. There we go. Okay. So we're going to check each of the 4 neighbors. We don't need to find them. We already know where they are. So if block, and what is that going to be? What is our X and Y position even going to be right now? Our leaf position is going to be, yeah, so leaf list X. There we go. Leaf list leaf list. Okay, apparently I've created a tongue twister. J, comma, leaf Y, J. So that's our X and Y position. And let me see. True was empty, right? Was true empty? Is it going to do... The false is all the solid walls, right? Or the false was the open ones. I think the false was the open ones. Okay. So if it's an open thing and it's not already used, right? So we want to go if it's open and it's not already used. And so not already used is going to be, let's see, what is that going to, where is our search cells in this same position. And you know what? I think we're going to have an issue here with, why is it doing that? And you know what? I think we're not going to need the search cells to be all the way down here, are we? I think we can actually have that in. I think we can have that. Yeah, let's do this. Let's do this, and we can take this out. Let's get rid of this up here. We can go to up here, and let's see, that's going to be with all this stuff. because we're not going to need to save that after we're done with this search, so we don't need to do that. Okay. So why is this? Oh, okay. Is less than 0. There we go. So we're going to start all of those at. We're going to start all those at -1, because if we started at -1, then we're going to have to go through and initialize all those, which is going to be an extra step. So why don't we equals 0? We can find a different way to decide that these have been used, if you know what I mean. So yeah, basically in this thing, they're all going to be 0 when we first start. And so then we're going to add a 1 and 2. So that way we know which ones have already been searched, have already been part of the search pattern. Okay, so we'll go, we've got that. So now the neighbor is empty and it has not already been used as part of the search, as it hasn't been filled in with our Floodfill. Then we're going to go, we need an incrementer. So we're going to go int trail length equals 1. And then we're going to go search cells. And you know something else we need to do here is we're not going to actually do this. This is the cell we're actually looking at. We don't want to look at ourselves. We want to look at the neighbor. Is that right? Yeah, we're going to look at the neighbor of the leaf, not the leaf itself. So we're going to go like this. We're going to take this out and we're going to do some numbers like temporary X and temporary Y. So let's go this int tx equals leaf list dot x minus 1, for example. Okay, int ty equals list y. So we're going to start on the left. Okay, and we're going to go tx comma ty, tx comma ty. Okay, so now we've got that. We're going to go search cells tx comma ty. The one thing IntelliSense can kind of work against you sometimes. Equals trail length. Okay, and then when we get to that, there we go. So if the neighbor is empty and already filled in, give it a search thing, and then we're also going to increment the trail counter. So we're going to go whoops, that's not what I was trying to do. Trail length plus plus. So once we've gotten all of our 1s, then we're going to be on the 2s, then we're going to be on the 3s, etc., etc. Okay? And so we're going to do this with each of these. So we're going to do this 4 times, and we're just going to copy paste 3, 4. Okay, and we're going to go left, and then we're going to go right, and then we're going to go up and down, or above, I guess, and below. So go like that, and then we need to make sure that we actually do to the right. So tx equals plus equals 2. We can do that, and then we can go let's see, tx minus equals 1 and ty minus equals 1, and that's going to put us back to the center and up 1, and then we're going to go ty plus equals 2, and that's going to be the one that's below. So like that. So that's going to give us all 4 of the things. We need to remove the one that we did from the leaf list. So we need to go or we need to just Do we need to create a new one? I'm just trying to think, do we need to create a new list now? Or, you know what? We don't need to remove it. We just need to increment our leaf counter. That's what we can do, because we're not going to go backwards to that. So each time we add one, we're just going to go to the next one. So we'll go int current leaf equals 0. Okay. And then we're just going to go there. So we're gonna basically iterate along the leaf list. Update. So basically we're going to go from 0, we're going to do number 1, we're going to add things on, and they're going to get added on at the beginning at least. They're going to get added on more quickly than we can even test. So like the first one's going to add 4 more, and then the next one, we're going to be on number 2, and it's going to add another 4 or 6 or whatever. So it's going to keep going like that. And we're going to check if current leaf is greater than, what is this? Leaf list x.length. Then we can done flag equals true. Okay, and so what we could do is we could actually simply limit our search length to say 100, and if it doesn't find anything within 100, well, too bad. Tough. Right? We could do that if we want to, and I'm guessing that's how, like, for example, Minecraft, they have a search distance of 40 or whatever, and I'm sure that's one way that you can limit that. You can limit your search length. So that's one of the ways. And then also if let's see, we also want to go or current leaf is greater than or equal to leaf count. Was it leaf count? Num leaves. Okay. Num leaves. And our num leaves is going to be the length of that. So yeah, our number here is actually going to be greater than the number. So it's going to be the number of things in the thing. So we're going to do that, and let me see here. I need to find where we're going to increment num leaves, because otherwise it's just going to stay at 1, isn't it? Each time we add a new leaf. So we're going to go leaf list x num leaves equals, that's going to be tx. Okay, and then we're going to go the same thing with y, because we need to add this to our list of leaves. And then we're also going to do num leaves plus plus. So we want to increment. It's important that you increment this number either before or after, depending on how you're going to treat it once you're, how you're going to use it later on. So that's why you got to pay attention to this stuff. And so this is where you get, the compiler is not going to tell you that you have an error. It's a logic error. It's not going to tell you that there's anything wrong. It's just going to run badly. It's just going to act stupid. Okay. And so I think that should give us all of our things. So how are we? This is just going through the num leaves, because this doesn't seem like it's gonna. Oh yeah, it is. No, it's not. This little for loop here isn't gonna work. So we're gonna go. Current leaf equals 0, because this j is just a problem here. J is our problem. Current leaf plus plus. Yeah, I think we don't need that whole loop. I think this whole loop was unnecessary. So let's go like this and it'll fix the indentation. There we go. Okay, for each leaf in the list, check each of the 4. Okay, and then this is going to check if there's any leaves left. Okay, so I think we are good there, and I think this will loop through until we have found our destination. And so when we've done that, now what we now also need to do is this is going to keep flood filling. We also need to check if any of the positions is the actual target. So we need to do this, and we're going to have to put that in each of these. So let's see here. Why don't we do that before we check all this left, right? I'm just trying to think of how we should do that. Let me see here. Oh, and we need to get rid of this J too, because we need to go current leaf and current leaf. I'm just trying to decide how we want to handle this. Checking if let's go if tx equals target x, right? I'm just trying to think if it's even worth checking each time here, or if we should just check with each leaf, because we're going to end up with more. Yeah, we're going to check it inside here. And is that I? I think that's I, yeah. Yeah, that's correct. And ty equals target y, I. Let's put this all in parentheses. And then what we want to do is we want to, one of the things is going to be done flag equals true. So we're going to put that in there, and I think that's actually it. Yeah. I don't think we need to do anything else. That's where we found it. Do we need to tell it we've been successful or anything? Because our current leaf, let me see, let's go. I'm just trying to think of how we're going to know once we've come out of this. We're going to have code down here that then assembles the trail from the last position to the target, because we started at the target, so that's actually not going to be correct, right? That's where we just started. Equals is it enemy? Where's the enemy positions? Where's the enemy's position? Let's find that. Enemy X. Okay, so that's what we're looking for. Equals enemy X. Oh, yeah. Duh. We'll definitely know. We'll definitely know where that is, because we'll be starting at enemy X and enemy Y. Right? So we'll go like this. Get rid of that and that. So we can do this and this and this. Okay, so if our target is that, then we're done. Then we found it. And so for right now, for the moment, we're just going to assume that it's always successful, that there's always going to be a path found to the thing, and we'll just start, assembling from there if we can. So we're going to go assemble the trail from the last position. I think we do, honestly, I think we are going to need a success aren't we? Why don't we just do that? Flag equals false. We're going to start with a success flag that's false, and then we're going to put this in here because I don't want to mess around with this. Success flag equals true. So the only time this is going to be true is if we did actively find, if we really did collide with self from here. So we're going to go like that, that, and that. Okay, so yeah, because see, if we do that and then done flag is true, then we don't have a thing. So I think what we'll try is we're going to go if success flag, else, not sure why it did that. There we go, else. Okay, just move randomly, right? Basically, just move around randomly. So if we are successful, we're going to assemble the trail from the last position to the target. So starting it at enemy Y, we're going to find the lowest neighbor. And so we're going to go while, let's see, what is it going to be? Our trail something. Best is greater than 0. So our, let's see, what are we going to set our trail best to? Equals a lot. Okay, let me see, int trail best. Okay, so that's, we're going to start looking for neighbors. So we're going to find the lowest we're gonna check the top versus the bottom versus the left versus the right, aren't we? So I think we're gonna end up with one of these ugly if-then nested if-then structures. So because we want to find the neighbor with the lowest value. So let's go if what is that going to be? Not enemy, it's going to be search, because that's going to be stored in this search cells thing. And we're going to go right tx and ty. We're going to use a tx and a ty again, and we're going to need to declare those two. And so if this is less than lowest trail best, that is. And we also need to make sure it's not a 0, right? And this is not 0, because if it's 0, then it was never flood filled in. And so it's not an actual valid, there's no valid path to it as far as we know. So we're going to nest all that. It's less than trail, and this is not equal 0. Okay. And if that, so let me see, we're going to do a dx and a dy too, aren't we? I think. Yeah, let's do this. Let's go int dx, and dy is going to be our winning directions. Okay. So dx equals, is this going to be, we're going to start the same way, we're going to go left, -1, and dy equals 0. So we can even do that, and we can go tx equals, what is that going to be? It's going to be, we're going to have a current position, right? Our current position is going to start with equals enemy x, and ty equals enemy y, and we need to put that in there. Whoops. Okay. Are you lost yet? Okay, so we're going to check to the left. Do I want to do D or T? Let's do check X and check Y, right? Is that what I want to do? I'm just losing track of which variables I've got here. Check to the left. We're going to go, because this is going to be kind of our center. Yeah, this is going to be where we're at. We don't want to lose this, right? We want to keep track of this, and we're going to check 4 positions from there, but we still need to come back to this. So we're going to go, yeah, we're going to go CX and CY, and CX and CY. And if that is the best one, then we're going to add that in. And we're missing a semicolon there. There we go. Because you know what happens when you miss a period or a semicolon. It doesn't work the same with semicolons. And so we're going to go like, I just wanted to make sure that this is actually what we want to do before I copy paste this 4 times. And we're going to check to the left, and then we're going to check to the right. And so we're going to go CX plus equals 2, and we're going to check to the right. And then we're going to go CX minus minus, whoops, and CY minus minus, and check to above. Whoops. I'm getting keywords here. And we're going to do one more below. And we're going to go CY plus equals 2. There. Okay. And then we also need to make sure, I almost forgot to do these. So if that's going to be X, it's going to be +1. Oops, that's just going to be 1. And this is going to be 0 and -1. And this is going to be 0 and 1. So we should start these out as equals 0 and dy equals 0. Because, you know, the thing that's kind of scary about this is that, no, there's no way that's not gonna, I don't think there's any way it's gonna not. The thing that concerns me is running into a situation where you don't have any valid things that trigger this, you know, and then you're trying to, you're basically caught in an infinite loop if none of these do trigger this. Because that's going to be that, and then our new TX. Now we've found the lowest, move that to the trail, breadcrumb trail, right? And update current pointer. So we're going to add this to our actual trail, our following trail. Now the question is, do we want to do this so that, do we actually want to create a big long trail, or do we just want to recalculate this each time? You know, do we want to do this whole flood fill every single tick and then just move the thing one and then do the whole flood fill and then move one more? Because I'm thinking what we can do is we can kind of optimize this by basically filling out this trail and then moving maybe 5 or 6 moves at a time along the trail until we update it again. You know, that kind of thing, so that we're not doing this every single tick, just to save some, you know, some work on that. Okay, so we're going to go, where is our trail length? Okay. Yeah, we have trail length, and what is the name of our variable for the enemy trail? There we go. Okay. So trail length plus plus, right? And what we're going to do is we want to go equals 0. We want to start that over. And we're going to go trail, what was it? Enemy trail. Enemy trail. And we're going to do our x comma y. See, that doesn't need to be a 2-dimensional array. I think we need to do, yeah, I think we're going to do x and y. So let's go change these. We'll go change this variable. Max enemies. I'm just trying to decide how I want to do that. Like that. X. So we're going to do that. And, whoops, and we're going to do that. I just want to arrange this in a way that's going to be easiest for me to figure out what I'm doing. And then we're going to go enemy trail. Where'd that go? Where'd our declaration for that go? So we're going to go enemy trail X and Y. There we go. Okay, so we have those. So this is the enemy number and this is the position. I should probably put a note on there. There we go. Okay, is that enemy? All right, and let's go back down here. And we're going to add in, let's see, enemy trail X, and then it's going to be I, right? Because that's our enemy number, and then trail length equals dx, tx plus dx, right? Tx plus dx. Okay, and then we're going to go, is that going to be our new, why don't we go dx plus equals tx, right? Is that what we want to do? We want to add that, and we're going to store that in dx. So go dx plus equals tx. So that'll give us our new positions, right? So dx is the sum of these two. So that way we're basically either subtracting or adding 1 to our thing. And we can do that. So this will save us an extra assignment later. And I need to go get a kitty out of here. So I will be right back in a second here. Come on, kitty. Let's go. All right. Yeah, she's fine to hang out on my lap, but she likes to get into everything. Okay. So we're going to do the trail of that, and then we're also going to I'm just trying to decide how are we going to keep this information for the next round. I think TX is where we're going to store it, isn't it? Yeah, so TX plus equals DX and TY plus equals DY, and then we're going to assign this. We're going to keep these out here. Whoops. There. So now when we do this, we're updating this every time. We're updating this value. And then we can go, should we do some kind of double check if dx equals 0 and dy equals 0? I think we should. If dx equals 0 and dy equals 0, we need to get out of this loop just in case. So that will get us out of this while loop so that we're not sitting here you know, going over and over from the same spot, because otherwise we're going to keep checking the same spot and we're going to get the same result every single time, and it's going to try to make this thing like huge. So now we've got our trail length. We've actually added this. Did we ever, I'm just wondering if we ever, let me see here. I'm just wondering if we ever initialize this so that it's not going to be a problem. Enemy trail. And should we go to some, what should we make our max trail? Let's just make it 40. Right? We're just going to call it, we're just going to hard code it to maybe 40 or 50. Why is it telling us that? Expected comma or comma? Really? Because it's this, right? Int enemy equals new. Why is it not letting us initialize it like that? Oh, it's because I'm trying to do the whole thing like that. Okay, so I need to go... yeah, we're just going to do that. We're going to overwrite this instead of creating a new and throwing away and doing all the garbage collection with that. We're just going to use the same array over and over and just kind of clear it out ourselves. So for I equals 0, I is less than max, whoops, max enemies, and we're going to go enemy trail x trail I equals new int 40. That should work. Okay, so that's going to give us 40, and we should probably do max trail length so that we can configure that, because otherwise if we need to come back and change that number, it's going to be a problem too. So why don't we go, where is all that stuff? Int max trail equals 40, just so that if we want to change it, it's easier to change it in one place. So we'll go like this. We can do the same thing with y. Okay, so now each of these one has been initialized to a whole array of 40. Okay. All right, and you know what? Do I need to make that a jagged array? I'm not sure. That's going to be something that number and then that number. Actually, I could do it the other way. But I think this will, yeah, it won't make a difference. It's just the way we address it. So let's go like down here. I know in accessing it from memory, it will make a difference of how it accesses the actual elements in the array. So if you're incrementing this one by one, I think it's actually faster to do this jagged array. But anyway, so what we're going to do is we're going to go trail length plus plus that, and then or trail length is greater than or equal to max trail length. There we go. So that way we're not going past the end of this. And I'm kind of thinking, because that is 0, yeah. So that's going to be 1. So when that hits 40, I'm kind of thinking we need to do that, is what I'm thinking. Because then if it's greater than, because that's going to be, if we initialize it as 40, then when this hits 39, we're done. We have to stop when it hits 39, when it equals 39. Yeah, that's correct. Okay. So I think that should do it, and that should give us our trail length. That should give us an actual trail. We should now have a populated trail. X and Y now contains the XY of the trail cells. Okay. Of the desired path. Now the other thing that we need for each enemy then is going to be enemy trail position equals 0, and we're going to need to make this a variable, and we're going to need to keep that, and we're actually going to need to make that a, let me see, enemy trail position there, and then we're going to go enemy trail position equals new. What is that going to be? Max trailer length? Max enemies. Yeah, because it's just going to be a number that points to where they are on the trail. So that way we know, you know, when the enemies first starts, they're going to be on position 1. And so, yeah, our array is going to be, where'd that go? So our array is going to basically end up being a set of, X and Y coordinates. We're going to have an X array and a Y array, and our trail list is going to be this, and then this, and then this, and then this, and then this. You know, these are going to be X, Y coordinates that are filled in, so that's going to correspond to like here, and then this one's going to correspond to here, etc. So we need our little pointer is going to point to which one of these cells were actually, points in the trail. So that way, each time the enemy moves, we know where to look for the next position. So that's what that's for. So that's what this enemy trail position is going to be. And so we need to come back down here, and we need to go high. So that's resetting that. Now we need to decide when the enemy needs to make a new trail. It's another thing we need to do here because we're not going to do this every single time. Yeah, okay, so that's that. When enemy needs it, and we'll probably need to add in a we need to add in a check to see if end of trail is hit. Okay, so yeah, we'll be doing that instead of this enemy line thing. But yeah, we'll check to see if the end of the trail is hit. Now I like to do this because then I can do a find later in my code for fix me : and it'll find all of the little notes that I put in my thing as to, I need to do this or that. So that's what that is. If you use the same spelling and everything every single time, and it's something that only appears there and never anywhere else, then you can find all your little notes of things that you need to do. So when you go back to your code to fix things and stuff. So actually, I think we can code that. Can we code that right now? If enemy trail position, enemy trail position I is greater than or equal to enemy. There's a trail length, right? We just added a trail length of some kind. Yeah. Aha, we don't have an enemy trail length, do we? We're going to need that because that's actually going to need to be in here, or we can just do enemy trail x dot length. Okay. Enemy trail x I dot length. So yeah, so if that is that, or yeah, we should leave in the line as less than or equal to 0. We should still do that, because what we can do is we can have it do a trail. And it's not going to go to the whole trail, because by the time it gets there, the player's going to be long gone. So we'll have it check like every 5 times or something. So we need to find out where the enemy line is getting reset. If enemy line is blah, 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 enemy line equals... Okay, yeah, so there we go. That's going to still set that up. All right. It's going to set it up to be 10. And so we can let it do that for right now. We can let it do 10 movements. And so I think we've got everything set up. This we need to we're just going to leave this for right now. We're not going to code all that stuff in. And I think we've got everything set up here. And we just need to figure out where next move wants to be along the current path. So enemy trail position I. So what is that going to be? Right. So equals, we're going to get rid of that. So enemy x I plus equals, and we're going to go enemy trail x, enemy trail position, I, right? And we also need to go I here, because that's for this enemy, and then a trail position. Yeah, this same enemy's trail position. And I think that will give us our number. And we can do the same thing for the Y. And we need to make sure we change both of the Y's. There we go. We can get rid of this. And we shouldn't need to check these either. Right? We shouldn't need to check those either. Let's get that. I'm going to put that, I'm going to paste that somewhere else. And in the new position, which we already did. Okay, so we're going to need to check for collisions with player later, but I wanted to try this because we've been doing this for a long time now, and we're pretty much running way long today. So let's try this and see if it even runs. If it just crashes or whatever, right? Oh, I should have drank that before it got cold. Okay, we've got some kind of problem. If search cells equals -1 equals 1. Okay, so here's going to be our problem right here. Our tx is -1. So apparently we are, yeah. So we're going to have to make this check against the boundaries of the, let me see here. We're going to have to make this check against the boundaries. If tx is less than 0, tx equals 0, else if tx is greater than, what is it, max cells? Max size is greater than or equal to max size, then tx equals max size. There. And I just want to cram all this on one line because I'm lazy. And then we're going to go the same thing with ty and make sure all of them are switched over to y. You guys know why I'm laughing about that, right? It's not like it ever happens every other time. Okay, so what do we have now? We have 1 and negative. How is y -1? How is y possibly -1? So leaf list 2. So that's 1. And then this is, see, -1 and 1. Because y is -1. Because our first one, right? Our first position is current leaf 2, which is here. Oh, it's 0. It's a 0, and so how is that? Oh, okay, so we need to go if it's less than 1. That's why. Yeah, we need to make this bigger. Less than 1 equals 1. We're going to make it not search if ty is greater than or equal to max size -1. We're going to limit this stuff so that it can't do the very outside. Okay, so let's try it again, and let's see if we can get this. I just want to let's see what we have now. Yeah, see, we're still running into negatives and stuff. Oh, this is, why is it setting this to equal -1? It should be like dx -1. That's why. So dx -1 equals dx, right? Isn't that how we're going to do that? Yeah. Or is that tx? ty. See, I almost did the x and y mix up again. Okay. I think that's what we need to do. Yeah, that's what we need to do. Okay, let's try this again. We have a 9 and a 40. We have a 9 and a 40. Okay. Oh, 40 is out of bounds. How are we getting 40 then? So ty is, and what is the current leaf? 703. Okay, apparently, let's see if we can go -2 on this. Let's go -2. Let's see if that's going to do it. And now what are we getting? We're getting 40 on the x. How are we getting? Because if this is 40 minus 2 is 38, right? Apparently, we do need to do not -3. Okay. So that's 37. So this is starting out. Oh, that's right, because we're already doing 1 to the left. Okay, that's why. Because this is 1 to the left of where this is. You know what I mean? And so, yeah, let's try this. See what we're getting now. 19 and 40. We're still getting this. Okay. And that is the Y is still ending up at 40. DX is 0. So what is CX starting at if it's ending up, or CY is starting at? That's 40, 39, 38, 39. It's starting out at 39. So how is this happening? Okay, well I think we're gonna stop for here. I'm gonna look around with this. I will let you guys know what I figured out with it in the next time. So yeah, that's gonna be it for number 6. Join me in number 7. We'll get this thing working, and we'll see how it works. So yeah, thanks for sticking with me through this, and we'll see you in number 7. Later.